In this problem, we have to flatten a multi-level doubly linked list. So in a doubly linked list, we have a next pointer and a previous pointer. Here we have an additional pointer, and that is child pointer. So you can see this is just one linked list, one doubly linked list, and you will be given the reference of head node. So if you are given a pointer to the head node, you can traverse the complete linked list. It's the next one, it's previous, and this is child, and it has 3 levels here. So after flattening, we have to make them like normal doubly linked list. So all the child pointers should be null and it should appear in a straight line. So that is, they will have just previous and next pointers and no child pointers. So this entire thing will come here after 3. So 3 should be here, then all of its children should come here, and then 4 should come. Similarly for this case, these two are the children, this is the children linked list, so it should come after 8. So 7, 8, then 11, 12, then 9, 10, and then this complete thing should be merged here. So let's see one example, then it will be more clear what is the requirement. So this is the input, and this is a linked list node. So only difference is that in normal doubly linked list we have next and previous, here we have child also, and all 3 are themselves node pointers, same type as this node itself, and this is the input. So see the result here, till 3 it's same, then after 3 all its children will come, and then 4 is here, 4 is here, till 3 it's same, and here also it's flattened. So you can see a recursive solution coming out here. So it will call the flatten on its children, and this child may itself be multi-level linked list. It will again see that 8 has a child, so it will call flatten on this. Now this is already flattened, so it will directly get inserted. So this will become 7, 8, then 11, 12, then this 9, 10 will follow. So this is flattened to this. Now the calling function, this will return to the calling function, this recursive function. So this returned here, and this entire thing after flattening will return here, and the job of this node is that, so this will be our current, and it will just insert this entire thing after itself. So it will keep a pointer of its next node, earlier next node, and this recursive function will return the tail node also, what was the last node. So it returns the tail node, and it knows what was its child node, it's 7. So it will make its next as 7, previous of 7 as this current node, and this is the tail. So next of tail as this next, and previous of next as this tail. So that way this entire thing will be inserted here. So let's write a formal code for this, how we will do it. So we will have a recursive function, let's call it flatten rec, and it will take a head pointer. So what it will do, current will be equal to head, and tail will also be equal to head, and we will continue till current is not null, not equal to null. Then what we will do, we will check for child, whether this current node has child or not. If it does not have any child, then move current to next. So if current has child, so this is not null, then what we will do, we will call this function on this recursive function on the child itself. So this is the child. So initially current is here. Let's also store next, and we can also store tail. So all are here, there is no child, so make current equal to next. So current will come now here, and next will come here. So next is always pointing to next of current. So next is here, current is here. Again we will check if it has child or not. No. So again advance the current. So now current comes here. So current is now here, and next is here. And now we check if it has child or not. Yes, it has. So before advancing current to next node, our job is to flatten this child and insert it here. So if current.child is present, then tail would equal to flatten rec. So we are calling this same function on its child. So this child is 7 and this is a doubly linked list, multi-layered doubly linked list in itself, and this is the head for this new list. So we will call flatten rec on child. So you can store a child here or you can pass current child. So this should return the tail last node so that we can make its next point to this. So ultimately this will return, let's say it flattens it out and returns here. So it returns 7, 8, 9, not 9, 7, 8, 11, 12, then 9, 10. So it returns this value and tail is pointing to this. Then what we will do, we will just need simple pointer changes. So we are here current. So current next. So this next is the green pointer and previous is the yellow pointer. So current next, or I should have written it in green. Current next equal to tail. So what happens after this? This green is pointing to current next should be child. It's a mistake here. So now this green is pointing to this child. So we have 1, 2, 3, and here this is pointing to 7. So this we have changed. Then what we need to change? Tail next. So next of 10 should be this 4. Next. So earlier next was 4 before we call this recursively. So this list remains as it is: 7, 8, 11, 12, 9, 10. And I am not drawing the arrows, but here we have both next and previous. 10, and this is the tail. So tail next becomes next, and next was 4. So 4 comes here. 4, and after 4 nothing will change. So 10's next is 4. So let me draw in green. So this has changed with this line of code. Then what we will do? Current child equal to null. So this will be gone. So earlier what was happening? This, when we changed this, its child was still pointing to this 7. We did not change this pointer. Now with setting it to null, this will be gone. Otherwise it will be invalid list. Now what remains? Child previous. We have not set the previous of this 7. So its previous should be this current. So again this is the current and this is 4 is next. So this also we will change. So child previous equal to current, and then we are done here. We have corrected these 2 pointers and also these 2 pointers. We have not added the previous of next as the tail. So it may be a case that this was the 3 was the last node. 3 these were not existing. In that case next would be null. So we will check if next is not null, then next previous equal to tail. So what will happen? This was next, its previous is not set yet. That is, its previous is still pointing to 3. So this is the current state now, and this is invalid. There is a invalid link, doubly linked list. So this previous should be pointing to 10. So we will make that change. But if next is null, then we will not do it. We don't need to do it. This 10 will be the last node. So that's all. And then we need to advance the current. So we have already flattened this part. So we can also advance current by one step. But it's better to jump directly here, since this is already flattened out. So we will not need to travel this part again. So what we will do current equal to tail here inside this, and then if current is there, then tail equal to current, since we have to return a tail also from this function. So ultimately we will return tail, and we will make sure that we never reach here. So it will be the just till current is valid, this tail will chase current and current will be advanced. When current becomes null, this tail will stop here. It will know that this is the last node, last valid node, and we will return that. So let's write the code for this in C++, Java and Python. It should not be very tough. This is the same example. I had just drawn it in simplified form. So we will need a recursive function which will return a tail. In this case, it's the function that should return the head. So let's define a function. We can also achieve that by using a static tail variable, and then that will be shared across different calls. So let's call it node star flatten rec for recursive, and node star head. And here what we will do, if head is there, it may be that this linked list is empty, then we will simply return head. If head is there, then call flatten rec on this head, and then return head. Now this is the main logic. Node star current and tail both are head. And then while current is not null, child equal to current child. And we also need to store the next, so that when the flattened child returns the tail, we will make the next of tail as the earlier next. So it's inserted between current and next. So if you see this diagram, this is the current 3 and next is 4. So whatever is the child node, this linked list, after flattening, this should be inserted in between current and next. So we need to store next, so that tail will be returned, and we will make the next of this will be returned as tail, next of tail as this next. So we are storing next here. And if child is there, then we will do those pointer exchanges and call it recursively. So this child is the first node of this next level of linked list. So it's acting as a head for that, and that will be flattened ultimately. If there is no child, what we will do, we will see here. If there is no child, then current equal to next. So current will just keep incrementing to next if there is no child. If there is child, then only we need to flatten it, and ultimately next will become null, since next is always one step ahead of current, and this loop will end, and finally we will return tail from this, since this recursive function is returning the last node. And let's write the other code here. So tail is returned to us. What we do, tail next is next. It should be very intuitive, whatever we had seen in the logic, 4 pointer exchanges. So we will write it. Tails next is next. Other thing is next's previous should be tail. So always we will do in pairs, but there may be case that next is null, last node, then in that case this should not be done. And current next is for now pointing to the next, so it should now point to child. And child should be null, obviously. And childs, let me write in together. So these two pairs together. Tails next is next and next previous is tail. So this happens in pair. Current's next is child and child's previous is current. And next we are making this child as null, and now we are advancing the current to tail, since we saw here that since this is already flattened and we have inserted it here, there is no point in moving current just by one step and again checking those things. This part is already flattened for us, so simply jump current to last tail, or you can even move to next. So current equal to tail. So this was just for your understanding that these things are occurring in pair. If next of A is B, then previous of B is A. Similarly here. And if current is there, then tail will become current. So tail should not become null, because we are setting here next of tail and other things. So tail should be the last valid node, and tail will always be there since we are moving to this function whenever there is child. Whenever we have a child, then only we are capturing it. Otherwise tail will be pointing to the current only. So that's it. Let's see. Okay. So this answer matches. If you want to test more test cases, then you can write it like this. Let's say we want to see this case, a different scenario where this child is the last node. That is, it's like 1, 2, then 3, 4, and this is null. Or maybe 4 is also not there, but its child is there. So how we will define it? It should be 1, 2 null, then 3 null, then 4. And again this works as expected, so let's submit. And the solution is accepted. And what will be the time complexity here? So we are starting from here, go to next, we found a child, so we come here, go to next, we found a child, we come here, go to next. This is pasted here in between, and we are not again coming to this. We are not double traversing these. We jump the current to the last or tail and we continue. Then ultimately this returns and we advance current from here to directly 10. So we are not visiting nodes multiple times, we are just visiting them once from beginning till the end. So if there are n nodes, it will be order n time complexity. And we are not using any extra space, only recursion stack will hold some values, but that is generally not counted in space complexity. But it's good that you understand that space will be occupied by that recursion stack. So if you are doing it iteratively using a stack, then there you would use similar amount of space. That can be of the order of n. If all the nodes are like this, like 2, 3, 4, there are no next, but only child, then ultimately this will call this will call this. So in the stack, all the nodes will be there. So space can be order n, time is also order n. Now let's write the same thing in Java. Not much change is required, and if you followed the explanation in C++, it should not be a big task here. And this solution works, so let's submit. And it's accepted in Java. Finally, we will do it in Python. And this also works as expected. So let's submit. And Python solution is also accepted.